Till now, we've only been looking at the properties of an image formed by concave mirror. However, there is one more type of a curved mirror. Do we know what it's called? Yes, a convex mirror. So what is a convex mirror? A mirror whose reflecting surface is curved outward is called a convex mirror. The question now is, how does an image formed by a convex mirror look like? Without further ado, let's find that out. We will draw a table on the right, just like we did for a concave mirror. Here is a convex mirror. Suppose an object is kept at a finite distance away from it. Look carefully at its image formed. Can you orally tell me the properties of the image by just looking at it? First of all, we conclude that the image is smaller in size compared to the object. This is very clear. The image is diminished. The light rays seem to come from the point behind the mirror. But obviously, we know that no image is formed there. So this is a virtual image. Also, it's an upright image. Remember that every virtual image is an upright image. What if I move the object towards the mirror? If I move the object towards the mirror, the size of the image keeps on increasing. But the size of the image with respect to the object is always smaller. What will happen if I move the object away from the mirror? As I move the object away from the mirror, the relative size of the image keeps on reducing. Also, at any finite distance away from the mirror, image formed is always a virtual image. You know what's coming next, don't you? Yes. What if the object is infinitely far away? Well, in the case of a concave mirror, when the object was infinitely far away, the image was formed at a single point. It was real, point-sized, and a highly diminished image. Point-sized means that the whole image of the object is formed at a single point. Here too, the same thing happens. Image formed is indeed point-sized. But here, the image is a virtual image. So when the object is kept at infinity, the image formed is virtual, point-sized, and highly diminished. Notice that even though the object is kept at infinity, the image is not at infinity. It is at a finite distance behind the mirror, even though the object is infinitely far away. In fact, this is the maximum distance at which image can be formed. Image in a convex mirror cannot be formed behind this point. We will now represent the image formed by a convex mirror using ray diagrams. Let's try to draw a ray diagram for this case first. This is when the object is at infinity. Our object will be the usual arrow, and suppose it's at infinity. Now if you remember, I told you that the rays of light coming from the object at infinity are considered to be parallel to each other. And we know that two rays are sufficient to draw a ray diagram, so we will take any two parallel rays striking the mirror. These rays will be reflected in such a way that laws of reflection are obeyed. We notice that the rays are diverging after reflection. And when we extend these rays backwards, they meet at a single point, which is the principal focus in this case. What does this imply? When we are looking at the image of an infinitely far away object, it appears to be formed at this single point behind the mirror. If the parallel rays are traveling in this direction, the image is still formed at a single point, which is different than the principal focus. We call this point focus, as it does not lie on the principal axis. What now? Now let's keep the object at a finite distance from the mirror and try to represent the image formed for this case using a ray diagram. So how did we proceed? We only need to take any 2 points on the object which is represented by this arrow. Find out the image of these two objects' points first by drawing at least 2 rays emerging from each point. After reflection, all these rays will follow the laws of reflection. When we extend these rays backwards, we get our image locations. I repeat again that this is not a real location in space. It's only a location where the image appears to be formed. I want to pause here for a moment to tell you the reason exactly why I chose these 2 rays only. One parallel to the principal axis and the other directed towards the focal point. Yes, these are not random 2 rays. I chose them on purpose. Well, if you remember, when we were talking about the ray diagrams for images formed by concave mirrors, we thought that the rays which are parallel to the mirror will always pass through the focal point after reflection, and the rays which pass through the focal point will always travel parallel to the principal axis after reflection. There, we had only used these two rays to draw all of our ray diagrams. But in convex mirrors, we know that the rays cannot pass through the focal point as it lies behind the mirror. But if I direct the incident ray towards the focal point, then after reflection, it travels parallel to the principal axis. Yes, any ray which is directed towards the focal point, it will travel parallel to the principal axis after reflection. Also, if the incident ray is traveling parallel to the principal axis, then after reflection, it will look as if it originated from the focal point. For instance, here, all these reflected rays seem to be coming from this focal point. With this bit of knowledge, let's jump back to where we were initially. Now I think you understood the reason behind my choice of these two rays. Okay, so let's quickly join these image points to get the complete image of the object. If we measure the length of the object and the image, we will find that the object's size is greater than its image. So we say that the image is diminished. Also, one more important thing that I must say is that the image's distance from the mirror is not the same as the object's distance from the mirror. If you remember, when we were discussing plane mirror images, the virtual image distance and object distance from the mirror were the same irrespective of where the object was placed. Here, even though it's a virtual image, it does not follow that property. So, these two are the ray diagrams representing the image and its properties. When the object is infinitely away from the mirror, we get a point-sized image at the focal point. And as we keep moving the object towards the mirror, the size of the image keeps increasing and it appears to be coming closer to the backside of the mirror. In the next video, we will see some uses of concave and convex mirrors in real life.